Welcome, welcome, welcome. How is everybody doing today? I'm just going to give you a little glimpse. I am here. I'm in a bedroom in my house, so I'm not bothering anybody. Just wanted to say hi. All right, enough with that. Our first lesson today I'm kind of excited about because it has to do with patterns. So our first whole chapter in geometry has to do with different tools that we're going to use throughout the whole year. Tools of geometry. So one of the first things we're going to do is talk about inductive reasoning. That's a fancy way to say observing the things around you and finding patterns. And as you know from my 6-word story, that's one of my favorite things, predictable patterns. So yay, I'm excited about this. Let me just give you a quick example. I know that you guys have found patterns before. So if I wrote out these numbers, and I asked you, what is the pattern here? If you take a look, first thing I notice is I know when I double 3 I get 6. And hey, when I double 6 I get 12. And when I double 12 I get 24. I know that right here every one of these are multiplied by 2 to get the next number. So I observed what was going on there and I found that pattern. Very simple. So we're going to practice some of that tomorrow, finding predictable patterns. Some of them are going to be easy, some of them are going to make you really have to think. So I'm excited to see how you think. Let's move on down. The next thing we're going to talk about is, and if I'm going too fast, remember that you can pause this and you can take the notes that you're supposed to on your whisk. So don't forget, taking notes is included in the watching, the W part. So you need to be writing this down. It helps put it in your brain. All right, another tool we're going to use in geometry, I'm just going to stay about right there, are conjectures. Conjectures, you probably know the word hypothesis a little bit better. A hypothesis is like a conjecture, except it's in science. And if you know what it is, it's a conclusion that you've reached based on the reasoning that you've done, the inductive reasoning that you've done. So I have an example of a mathematical conjecture here. All right, so let's take a look. Try to just leave this part on the page. Take a look at what I've written right here. If you take a look, 1, and 1 plus 3, 1 plus 3 plus 5, 1 plus 3 plus 5 plus 7, looks like I'm adding odd numbers. And if you look at the answer that I get, the sum, every time I get a sum, it ends up being the perfect square of however many add-ins I had. Here I have 1, the answer is 1, which is 1 squared. Next, 1 plus 3, the answer is 4. I have 2 add-ins, and 2 squared is 4. 1 plus 3 plus 5 equals 9. I have 3 add-ins right here, and 3 squared is 9. 1 plus 3 plus 5 plus 7 is 16. And I have 1, 2, 3, 4 add-ins. 4 squared is 16. So I'm going to make a conjecture using this inductive reasoning that I have looked at and investigated. I'm going to make a conclusion now. It's called a conjecture. I'm just going to keep saying that so you remember that in math. I'm going to conclude that the sum of the first, let's write this down. Oh, I'm in pink. I don't want to be in pink. I'm sorry about that. I want to be in this blue. All right, I'm going to make a conjecture that the sum of the first, I'm just going to bump way ahead, the first 30 odd. That is not looking like a D. Sorry, I told you I'm be getting used to using this equipment. Sum of the first 30 odd numbers is going to be 30 squared, because I'll have 30 add-ins, right? Just like I had 4 add-ins here and it ended up being 4 squared. Well, if I have 30 add-ins that I'm adding up, I'm going to make that conjecture, and I'm going to say that the sum of the first 30 odd numbers is 900. Now, I don't know it for sure because I haven't tested it yet. When you make a conjecture, it's a conclusion you've reached based on inductive reasoning. It's not fully tested and proved yet exactly, but you're pretty sure. So, you've got to test it. So when you test a conjecture, hopefully if you test this one, you'll find out that it's true. But if you test one and you find out it's not true, you found what's called a counterexample. Alright, so let's just take a look at what I have ready here. This is another one of our tools we're going to use. Testing conjectures and finding something, well, that proves it wrong, basically, is what a counterexample is. So this little chart I've made you can look and see. It looks like I've got multiples of 5 on here. Looks like that I've got 5 times 7 is 35. You can see what I have right here. And I'm going to make a conjecture just by looking at these and say that the product of any, the product is the word, what we call the answer to a multiplication problem. The product of, I'm going to change that word any. Hang on just a second. Didn't mean to write any. The product of 5, and if you take a notice, all of these are odd numbers, right? Okay. The product of 5 and any odd number will be odd. That's what I think. Now I would need to test it and see if that's true, and I do believe if you tested me on this one, it is true. I'm going to make another conjecture. Let's put a little dot right here. So there's 1. I'm going to make another conjecture too here. I'm going to say that the product of 5 and any number based on what I'm looking at ends in 5. Because all of these end in 5, don't they? So that's a pretty good conjecture. However, I can prove that that one's false because one of the very first ones is 5 times 2 and it equals 10. That is not a 5. So that proves this one wrong. Okay, it's a no. So this is what we're going to work on tomorrow. I love patterns. I think we'll have fun. Some of them are going to be challenging, so I'm looking forward to it. Thank you very much for watching and watching and taking notes. Don't forget your summary, short sentence on what we talked about today, and a question if you have one. Thank you very much. I'll talk to you tomorrow.